In mathematical analysis, the intermediate value theorem states that if a continuous function f with an interval, a, b, as its domain takes values f, a, and f, b, at each end of the interval, then it also takes any value between f, a, and f, b, at some point within the interval. This has two important specializations: 1, if a continuous function has values of opposite sign inside an interval, then it has a root in that interval. 2, the image of a continuous function over an interval is itself an interval. Motivation. This captures an intuitive property of continuous functions, given f continuous on 1, 2, with the known values f, 1, equals 3 and f, 2, equals 5. Then the graph of y equals f, x, must pass through the horizontal line y equals 4 while x moves from 1 to 2. It represents the idea that the graph of a continuous function on a closed interval can be drawn without lifting your pencil from the paper. Theorem. The intermediate value theorem states the following. Consider an interval I equals, a, b, in the real numbers a and a continuous function f, iaa. Then, version I if u is a number between f, a, and f, b. f, a, u, f, b. Then there is a ca such that f, c, equals u. Version 2. The image set f, I, is also an interval, and either it contains f, a, f, b, or it contains f, b, f, a. That is, f, I, f, a, f, b, f, b, f, a. Remark. Version 2 states that the set of function values has no gap. For any two function values C0. Since f is continuous, there is AI0 such that a euro f, x, af, c, a euro f, aai micro a per million uai micron. Both inequalities. Uai micron 0, from which we deduce f, c, equals u as the only possible value, as stated. An alternative proof may be found at non-standard calculus. History. For u equals 0 above, the statement is also known as Bolzano's theorem. This theorem was first proved by Bernard Bolzano in 1817. Augustin Louis Cauchy provided a proof in 1821. Both were inspired by the goal of formalizing the analysis of functions and the work of Joseph Louis Lagrange. The idea that continuous functions possess the intermediate value property has an earlier origin. Simon Stevin proved the intermediate value theorem for polynomials by providing an algorithm for constructing the decimal expansion of the solution. The algorithm iteratively subdivides the interval into 10 parts, producing an additional decimal digit at each step of the iteration. Before the formal definition of continuity was given, the intermediate value property was given as part of the definition of a continuous function. Proponents include Louis Arbogast, who assumed the functions to have no jumps, satisfy the intermediate value property and have increments whose sizes corresponded to the sizes of the increments of the variable. Earlier authors held the result to be intuitively obvious, and requiring no proof. The insight of Bolzano and Cauchy was to define a general notion of continuity, and to provide a proof based on such definitions. Generalizations. The intermediate value theorem can be seen as a consequence of the following two statements from topology: if x and y are topological spaces, f, x or y is continuous, and x is connected, then f, x, is connected. A subset of A is connected if and only if it is an interval. The intermediate value theorem generalizes in a natural way. Suppose that X is a connected topological space and equals 0. This function is not continuous at x equals 0 because the limit of f, x, as x tends to 0 does not exist. Yet the function has the intermediate value property. Another, more complicated example is given by the Conway base 13 function. Historically, this intermediate value property has been suggested as a definition for continuity of real-valued functions. This definition was not adopted. Darboux theorem states that all functions that result from the differentiation of some other function on some interval have the intermediate value property. Implications of theorem in real world. The theorem implies that on any great circle around the world, the temperature, pressure, elevation, carbon dioxide concentration, or any other similar scalar quantity which varies continuously, there will always exist two antipodal points that share the same value for that variable. Proof: take f to be any continuous function on a circle. Draw a line through the center of the circle, intersecting it at two opposite points A and B. Let D be defined by the difference f, A, AF, B. If the line is rotated 180 degrees, the value AD will be obtained instead. Due to the intermediate value theorem, there must be some intermediate rotation angle for which D equals 0, and as a consequence f, A, equals f, B, at this angle. This is a special case of a more general result called the Bohr-Schuco-Ulam theorem. Another generalization for which this holds is for any closed convex n-dimensional shape. Specifically, for any continuous function whose domain is the given shape, and any point inside the shape, there exist two antipodal points with respect to the given point whose functional value is the same. The proof is identical to the one given above. The theorem also underpins the explanation of why rotating a wobbly table will bring it to stability. See also, mean value theorem, Hairy-Ball theorem, Bohr fixed point theorem. References: Weierstein, Eric W., Bolzano's theorem, MathWorld. Essentially follows Clark, Douglas. Foundations of Analysis. Appleton Century Crofts. Pages 284. Grabiner, Judith 5, Who Gave You the Epsilon? Cauchy and the Origins of Rigorous Calculus. The American Mathematical Monthly 90, 185 €194 doi, 10.2307/2975545. JSTOR 2975545. Karen U. Sadi Katz and Mikhail G. Katz. A Burgessian Critique of Nominalistic Tendencies in Contemporary Mathematics and Its Historiography. Foundations of Science doi, 10.1007 per second 10699-011-9223-1. Link, O'Connor, John J. Robertson, Edmund F., Intermediate Value Theorem, Maxshooter History of Mathematics Archive, University of St Andrews. Keith Devlin. How to Stabilize a Wobbly Table. External links: Intermediate Value Theorem at ProofWiki, Intermediate Value Theorem, Bolzano Theorem at Cut the Knot, Bolzano's Theorem by Julio Cesar de la Incera, Wolfram Demonstrations Project. Weierstein, Eric W., Intermediate Value Theorem, MathWorld. Two-dimensional version of the Intermediate Value Theorem, by Jim Belk at MathStack Exchange. Mysore System Proof, http mysore.org. April 5 HTML T4.